Okay, here we are. Motion in 2 and 3 dimensions. Basically, we're going to do the exact same thing, just in 2 dimensions. Now, basically, the most important thing you could possibly know, I'm going to come over here, is if something is moving like this, it has a vector that describes how it moves this way, and a vector how it describes how it moves this way. And see how it's perpendicular? Okay, those two are completely independent. So if you throw a ball up and down, up and down, up and down, up and down, and then you throw a ball, or you roll a ball this way, okay, those are independent, right? And you're like, yeah, clearly, because I'm rolling it one way and I'm throwing it up. Okay, so this is a little weird, but if you throw a ball up and then you roll it with the same, like, let's pretend I'm gonna throw it up with this force of, I don't know, a lot. Hardcore throw and little bit roll. Okay? So I can hardcore throw and it goes poop, and I can little bit roll and it goes poop. But I can do both at the same time, but the two act independently of each other. So I can do itty bitty roll and it goes itty bitty roll. And I can do giant throw and it does giant throw, and then as a result, it ends up doing something like this. Okay? Whereas if I do itty bitty throw and giant roll, it'll do this. Okay? I wish that I had a better way of explaining that. But giant throw, itty bitty roll, itty bitty throw, giant roll. Okay? So they are treated independently, so you can basically solve, and what's really amazing about this is that you can solve the up and down problem, and then you can solve the lefty-righty problem, and sometimes you solve part of the lefty-righty problem, and then you solve part of the uppy-downy problem. But this is huge, because when you go into doing more cool physicsy stuff, statics, dynamics, engineering, physics, blah, 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 basically what you can do is you can be like, I'm going to look at movement in the x direction, and you can blah, 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 blah. Then I'm going to look at movement or position or acceleration or forces in the y direction, and blah, blah, blah. So instead of movement, I could also write forces, displacement, basically anything that's a vector, acceleration, eventually momentum, anything like that in the x direction, and I can do math. And then I can look at the y and do math. Now, sometimes it might be like, well, the y matters because eventually it falls to the ground, and once it falls to the ground, then it explodes or whatever, and then that affects what it does in the x direction. But insofar as, like, how it's moving, the movement is independent. And this is huge. Now, I'm saying x and y, but I also mean x, y, and z. So x, y, and z. Okay, if you ever wonder how that looks, so if you think about, you have an x and a y coordinate system, imagine if you're like Superman, you got a little cape, and you're looking down with your goggles, you see y going up and x going off to the right, and z is coming out of the page towards you. Okay, so then I'm over here as a normal human, and I'm looking and I see y is up, x is to the right, and then z is coming out of the page, like out of the page toward me. So this is like I'm seeing the arrow of z coming out of the page toward me. So z is at you. Another way to think about it is your fingers, like with the right hand rule for the cross product. So your fingers go this way. So this is a hand. Finger. Look at your fingers. These are horrible fingers. Your fingers go in the x, and then they curl around the y-axis, not a drawer, and then your thumb points out at you. I don't know what that's supposed to be a picture of, but here your thumb is pointing at you. So fingers in this direction, they curl around, they curl around, thumbs in the X, curl curl in the y direction, curl in the y direction. So here's your fingers, and then your thumb goes up here. There's your thumbnail. So you got a thumbnail. And then your hand is like this. See? I'm a drawer person. Okay. So that's really the most important thing you can learn to move forward in this, is that everything is independent. X motion is independent of Y motion, is independent of Z motion, with the caveat of like, well, once it hits the ground, then it kind of stops moving, or, you know, once it explodes, other stuff happens. But what we're going to do is we're going to separate, and that's kind of like why we did all this stuff in that other chapter where we were separating vectors into X component and Y component. Be like, you know, this vector is 3i hat plus 5j hat, is because now we can treat the I hats and do all the things with the I hats, and then we can do all the things with the j hats, and it's pretty awesome. So for example, when we were talking about rolling the ball and throwing the ball, if I'm rolling the ball, there's no gravity, right? So if I'm rolling the ball, there's no gravity, so acceleration is 0. So for all of my motion in the lefty-righty direction, A is 0. But if I'm throwing it up, then gravity is negative 9.81 meters per second squared, or negative 32.2 meters per second squared. So you'll see people do this, AX, AY, because in the X direction there's no gravity, in the Y direction there is gravity. Okay, but really what we're trying to do is to get your brain to kind of separate out the idea that you do X, Y, Y, and then sometimes you have to do a little bit of both at the same time, and, you know, that's just how it is. But if you can kind of mostly keep it organized that way, it should marginally help. Okay, so this is what this is talking about, is basically that you can have a vector that is expressing itself as like, so we call R of t is like a position, is a function with respect to time. So like at time 30 seconds, what's my position, right? And then there is an X descriptor in the I hat direction, a Y descriptor in the J hat direction, and a Z descriptor in the K hat direction. So basically, like, this is how far you are along this way, the Y, that's X, and then Y, you know, Y, and then, you know, Z would be coming out of the page. Oops. Z would be coming out of the, you can't tell what color that is anymore. Z would be coming out of the page. So out of the page is Z. Okay, so if I wanted 30 seconds, I could plug 30 into each one of those T's, but I can treat each one of these functions kind of separately when I'm doing the physics and the mathy stuff, and that's like the biggest, most important, oh my god thing for physics. Okay, is that, and the reason that this is true is because these are at right angles to each other. If they weren't at right angles, and yes, you can have coordinate systems that are wonky, cattywampus coordinate systems, which are super fun and delightful to use, but because this is physics 1 and we're just slow rolling into this, everything's orthogonal, everything's at 90 degrees, everything's amazing, and I know it doesn't seem like everything's amazing right now, but I swear it is. So that's what we got going on. Okay, so that's our position vector, is always considered R. All right, now, shockingly, if I have a function, or a, you know, an R, so if I have some kind of R1, and then I have an R2, the resultant is this one, right? Resultant. So I know that my resultant is R1 plus R2. Now, that always made sense to me. What are they doing here? This is doing the displacement vector, which is the difference between the two of them. So that is different than what we're looking at here. So I don't want you memorizing these equations, okay? So in the previous section, we were doing resultants, where it's like, this goes this way, that is the resultant, okay? What this equation here is talking about is the displacement vector of like, if I saw it here and then I saw it here, where is it going? Okay, and the reason that we care is because here in a minute, we're going to take a differential, maybe, eventually. Yes, okay. So basically, let's pretend we have this R1, and then we have R2, and we have R3. So what your book is saying here is this differential is like your delta R. And then here's another delta R. And then, you know, you can keep making lots and lots of these delta R's. R4. Okay, so a bunch of these little delta R's. Make sense, sort of? I'm trying to avoid doing a whole bunch of equations. If you like the equations, go read the book. That's what it's there for. But, okay, so what they're trying to show is this displacement vector, like kind of how do you change on average. So, you know, R2 minus R1 is the change. 2 minus 1 is the change, which also kind of makes sense because if you just look at it like this as a an old-fashioned addition problem, you could be like R1 plus delta R equals R2. Make sense? Maybe? Maybe, maybe not. Some people like that. Some people just like saying delta R equals R2 minus R1. But look, that's mathematically equivalent. Maybe, maybe, maybe not. But really, we don't care about this. This delta R stuff is just jibber jabber to get us ready for what really matters. And that's the idea that if we have a whole bunch of these R's going to a whole bunch of these positions over time, what in the world do you think that those little deltas are going to look like? And if you said slopes or derivatives, I can't spell, then you were right. So if I have a whole bunch of these position vectors and I want to know where is it going, how is it, what is the change in the position vector super as duper small, so really as delta something approaches 0. So as it gets tiny, 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 then what we would basically just do is we'll define that as the instantaneous velocity. So the velocity is dr dt, which we already knew, except before we were doing it in one dimension, and now we're doing it in multiple dimensions. And I've never, ever, ever in my entire life met a student who deeply, deeply cared that before we were doing it in one dimension and now we're doing it in an infinite number of dimensions. But now that's what's happened, okay? Now for the purposes of this class, okay, I'm going to show you something funny. In real life, since I have x as a function of t, I hat, plus y as a function of t, j hat, plus z as a function of t, k hat, if I actually took the derivative of this, and you'll do this if you ever take statics or dynamics, I could get velocity is the derivative of dx dt I, but then I have to chain rule it, di hat dt. So this would be like, if you have a rotating reference frame, then like, what if you've got your system here, but it's like a propeller and it's rotating and it's flying through space, then all kinds of things go to hell. And none of that is happening here. So we have this wonderful situation where velocity is simply dx dt in the I hat direction plus dy dt in the j hat direction and dz dt in the k hat direction. Does that make sense? So in case I don't think this ever would ever occur to anyone unless they were just super duper into it. But the idea is that, yes, in theory, you could chain rule this and you could have di hat dt, because you could have a rotating reference frame, but we are not rotating our reference frame. We are just trying to tie our shoes in physics, and it's going to be amazing. But we take the derivative of position, we get velocity. It worked in 1D, it still works in 2D. And that is literally the point, I believe, of this whole section. And velocity average is the difference in the velocity vector. Independence of perpendicular motion. Okay, we already talked about that. So, doop-de-doop-de-doo. And then we get to 4.2. And I feel like they're not doing anything super duper fun in this, except just to say, see that? We already wrote that. And then the average. So if you just wanted to do like a boring average, it's the 2 positions divided by the total time. So we were already doing that in 1D. Now you're just doing it in 2D. I don't find this terribly desperately fascinating, but this part. I think the other stuff I talked about is desperately fascinating, and you super duper need to know that. But it kind of gets lost when you're reading the book because you can't tell, well, what's the most really important key takeaway that I need to have. So hopefully that's enough to kind of get you introduced into the material.